In this lesson, I want to talk to you about waves, and especially I want to practice going through the wave equation to calculate energy or frequency or wavelength, any of those things. But let's start with the concept of a transverse wave. All EMR waves are transverse. So they look like this picture you see here on the screen. You may have learned in middle school the major parts of a transverse wave, but let's go through them one more time just to make sure. So first of all, you see this dotted line in the middle of the screen. That is called the baseline. It's the zero energy line. Think of like maybe if you're holding a slinky between two people and you're not doing anything, so the slinky is just kind of lying there, not doing much, not moving. That would be the baseline. But when you start moving it up and down, you're going to see this transverse pattern. That represents a displacement or energy above or below the baseline. So again, the baseline is just zero energy. Any transverse wave has a point, a lowest point, and we call that the trough. And opposite of that, the highest point of a transverse wave is called the crest. Then we have displacement above or below the baseline, and that has some relationship with the energy contained in the wave, and we call that the amplitude. Make sure you understand that the amplitude is only the distance above or below the baseline to the highest or lowest point. It is not the entire length or the entire height of one of these mountainous looking things here. Okay? So each of those would be an amplitude. And then of all of these, the most important property is the distance between two crests or two troughs, and we call that the wavelength. The wavelength is very, very important. Electromagnetic waves are self-propagating waves. They are alternating electric and magnetic fields that are perpendicular to each other, kind of like you see in this picture here. So they kind of move on their own through the interactions of those fields. You'll learn more about that in physics. Again, we're very concerned with the wavelength here. It's one of our three major properties of a wave. In the electromagnetic spectrum, waves vary from very long wavelengths to very short. So radio waves would have a long distance between two peaks, and a gamma ray would be extraordinarily short. Another very important property of waves, and transverse waves in particular, is frequency. By definition, the frequency is number of waves passing a point per unit of time. Now, we didn't really draw that into our diagram because it's very hard to represent a property such as frequency that has to do with movement of the wave on a piece of paper. So you just imagine you're a person maybe standing right here, and if you face left, what you would do is count to 1 and see how many of these wavelengths or how many of these peaks pass you in that amount of time, and that's an idea of the frequency. For waves traveling at the same velocity, longer wavelengths mean smaller frequency, and that's the relationship we have with EMR. Did you remember the EMR spectrum from middle school? Well, here's a different way to show it. We have on the far left radio waves and on the far right gamma rays. You can see that the wavelength increases as you go toward radio, and then the energy increases as you go toward gamma, and that would also indicate frequency as well as energy. These two diagrams are much more representative of a typical EMR spectrum, especially this bottom one. I want you to kind of file it away, maybe even print it out and use it. But you can see here on the top there's wavelengths, and from left to right the numbers are getting smaller, and frequencies on the bottom, and from left to right the numbers are getting larger. That shows an inverse relationship that I'm about to get into. For wavelength and frequency, I just mentioned those properties are inverse of each other. If you graph them on an XY graph, this is kind of the shape you would get. We see inverse relationships several times this year in pre-AP chemistry. Because we're dealing with EMR, all of those types of radiation I showed you on the graph, the radio, the microwave, the color blue, UV, X-ray, they're all moving at the same speed that we call the speed of light, and that is 3.0 times 10 to the 8 meters per second. That's 300 million meters in every 1 second. And this equation is the one we'll be using to solve problems when we're trying to find a wavelength or find a frequency given just the other property. The other relationship that's important for EMR waves is the relationship between energy and frequency. This time, the relationship is direct. So if you graph it, you would get a linear graph this time. And like any linear graph that you've ever done in math, you have a slope. And the slope is a proportionality constant. It tells you exactly how the rise over run is changing, or exactly how these two variables are related to each other. Well, it turns out the slope for this is a number value, 6.626 times 10 to the minus 34th joule seconds. And we call that Planck's constant, symbolized by lowercase h. And the equation that we have here is very similar to a y equals mx type of thing, E equals hf, and that's how you calculate the energy of a photon. So now we have some problems that we're going to work through together. I'll show you how to set them up. You may want to copy this page out and hit pause and do one, and then hit play and see if you got it right. Let's get to work on these problems. Notice at the bottom of the page I've given you kind of a reference of the constants and their values. Don't be afraid to hit stop at any time or hit pause and go down and look at those. Number one, a photon has a frequency of 2.68 times 10 to the 6 hertz. Calculate its energy. Well, we know that energy is E equals hf. I'm using F for frequency. The problem here uses the Greek letter nu. I don't like nu because it looks like V for velocity. I think it confuses you, so I'm going to use F for frequency. So to calculate the energy, I only need to know the value of frequency because h is a constant. It's Planck's constant. So 10 to the minus 34. Let's make a better 3 there. Joule seconds. And the frequency is 2.68 times 10 to the 6th. And a hertz is a 1 over second. So the seconds here will cancel, and that'll leave me an answer in joules, which is exactly what I'm looking for. Get your calculators out, and the answer to this problem is 1.78 times 10 to the minus 27 joules. That would probably be a radio wave, or most likely a radio wave. I don't think it would even be a microwave. All right, and then problem number 2, calculate the energy and the wavelength of a photon of light with a frequency of 6.165 10 to the 14th hertz. So again, energy is going to equal Planck's constant, 626 10 to the minus 34. And we plug in 6.165 times 10 to the 14th. And for this one, we get the energy equal 4.1 times 10 to the minus 19th joules. 10 to the minus 19th is a very common power for the photons that we deal with in chemistry. If you ever get that answer, you should feel pretty good about it. Okay, in problem 2, we're also asked to find the wavelength. So that's a different relationship. This is a C equals lambda F. Lambda is wavelength. For every problem dealing with finding wavelength or frequency when you're given the other, it's always going to turn out to be the speed of light divided by the value you're given to find the one you're missing. So for our problem, we know the speed of light. We always know the speed of light. And that's a meter per second. And we're going to divide that by the frequency here, which is 6.165 times 10 to the 14th. And a hertz is 1 over seconds. So here the seconds cancel. And we're left with a wavelength of 4.87 times 10 to the minus 7 meters. Let me write that a little more neatly. 4.87 times 10 to the minus 7 meters. Okay, on problem number 3, we're going to calculate the frequency and then the energy of blue light that has a wavelength of 400 nanometers. Well, before I get started on this problem, if you look at the units that we're dealing with, let's go down to the bottom of the page. Look at C. C is in meters per second, and then our Planck's constant energies are in joules, which are also made up of meters. Long story short, what I'm trying to say here is that you can't plug in nanometers into either of these equations. So you will always need to transfer out of nanometers or micrometers or picometers into just regular old meters. So going back from what we learned in Unit 1, 400 times 10 to the minus 9 and we're going to go over to the left 2, so plus 2. That equals 4 times 10 to the minus 7 meters. Alright, so now let's calculate first the frequency. So the frequency is going to be C divided by the wavelength to give us F. 3 times 10 to the 8th, which is the speed of light, over 4 times 10 to the minus 7. And I got 7.5 times 10 to the 14th, 1 over seconds, which is a hertz. Okay, and then in number 3, the second part where we want to find the energy is equal to Planck's constant, 626 times 10 to the minus 34. And now that we've got the frequency calculated, we can just use that number. 10 to the 14th. And that gives us an energy of this blue photon, or blue light, 4.97 times 10 to the minus 19th joules. All right, I'm going to give you a chance to do number 4. Hit pause, work number 4, and I'll give you the answers on the screen. Alrighty, number 4, I hope you got that lambda equals 2.0 times 10 to the minus 7 meters, which would be 200 nanometers, and then the energy of the photon is 9.95 times 10 to the minus 19th joules. Number 5 is going to be a little different. This time, we're given the wavelength, and we want to find energy. So we don't have a formula that has an energy just when you know wavelength, but we can make one. So let's go over to the side here and let's look at what we can do. We know that energy is equal to HF, and then I know that C is equal to lambda F. Well, if I had some way to transfer in a wavelength for frequency, I'd be in business. So let's go to this other equation here and let's solve for F. C over lambda is equal to F. Now let me substitute in the other equation for F. E will equal H now times C over lambda. And if we combine those terms to make it look a little neater, E equals HC over lambda. So that is how we can find the energy of a photon when we have wavelength and not frequency. It's a little bit more calculation, but you can still do it. So for problem 5, let's plug in our values. 6.626 10 to the minus 34, and then 3 times 10 to the 8 for the speed of light, all divided by the wavelength, which is 0.050 meters. So for problem 5, the energy comes out to be 3.98 times 10 to the minus 22 joules. Okay, for the rest of these, I want you to hit pause and I want you to try to calculate them using these formulas and these constants at the bottom of the page. And then when you think you've got them, hit play again and let's check your answers. Okay, check your work. Number 6 is a little different. You had to calculate the energy using the E equals HC over lambda formula. And then you just divided 1 kilojoules. Of course, you had to change that to 1,000 joules and then divide it by your answer to get 5 times 10 to the 22nd. And then the rest of the numbers, the rest of the answers are pretty straightforward. If you're not sure what you're doing wrong and still having any confusions, just come by and let me know and we'll work on it together.